Thank you, David, for the invitation. I feel really honored to give this talk, especially because it involves work done in collaboration with Carl. Part of this work has already been published in what I think was one of his last papers, and the second part is still unpublished, but is a continuation of things we did together. The outline of the talk is the following. First, I will give a brief introduction to the visual system, comparing differences between rodents and higher mammals, such as cats or monkeys. Then I will introduce the network model based on the hypothesis of random connectivity and compare its results with experiments. This is the part that is already published. Later, I will talk about work in progress, about the statistics of the thalamic input, also comparing with experimental results. Finally, I will summarize with the conclusions and ongoing work. Well, in the visual system, the image is generated in the retina, and then it travels via the optic nerve to the lateral geniculate nucleus. And from there, it goes to the primary visual cortex that is in the occipital region of the brain. These are the relevant circuits of the cortex. I will be mainly interested in the behavior of the neurons in the thalamus, the behavior of the neurons in layer 4 of B1, and in the connections between them. I mean, the connections that go from the thalamus to the to layer 4 in B1. The behavior, the response of the neurons in B1 has been studied since the 50s. Hubel and Wiesel discovered that when the stimulus is a moving bar, the activity of the neurons is strongly modulated by the orientation of the bar, as we can see in the right panel. The orientation for which the neuron generates more spikes is called the preferred orientation of this neuron. Hubel and Wiesel also speculated that this behavior could be explained via a specific geometric arrangement of the connections that go from LGN to B1, where LGN neurons that feed on a given neuron in B1 should be arranged on a straight line. In this way, this gives rise, obviously, to some preferred orientation for the stimulus. Let us note the on-off structure of the receptive field of the LGN cells, right? This will be important later. The stimulus can also be disintegrated instead of a bar, characterized by some average luminosity, contrast, wavelength, angle, and velocity. So this is the expression that the expression that we'll use for the luminosity field. So when I make the experiments, we can record some measured output. This measured output is called R theta of t. It could be a firing rate, it could be a membrane potential, it could be thalamic peak, the total thalamic input, etc., etc. Anyway, whatever it is, this quantity, I can always decompose it in Fourier components in time with the frequency of the stimulus. The first Fourier component that is the average response is called the F0. The first Fourier component, the second Fourier component with the frequency of the stimulus is called the F1, and there could be a higher order harmonics that are called F2, F3, etc. In this way, changing the orientation of the grating, we can obtain tuning curves. For instance, this is a tuning curve for the cat. In the right panel, we see some examples of tuning curves for the monkey. In all cases, we can see that each neuron has its preferred orientation. Now, if we plot the preferred orientation of the neuron on the cortex with the color code given by the panel in the right, we see that a very specific structure emerges that is called an orientation map. Neurons that are near in space have very similar preferred orientations. Now, what's the behavior in rodents? For instance, in mice. In mice, neurons are also orientation selective. Here we have tuning curves from a paper of Neal and Stryker of one excitatory neuron and one inhibitory neuron, showing that the activity is indeed modulated by the angle of the grating. However, if we plot the preferred orientation for different neurons on the cortex, we see a very different structures. If we compare to cats or monkeys, here in the left we have an example of cat, and in the right an example of mice. In mice, we observe a structure that is called salt and pepper. Because neighboring neurons have apparently a quite different preferred orientation. So, in some sense, in rodents, the system is more random, right? But one could ask if connectivity is totally random, can we still have selectivity? Or maybe some specificity is needed in the connections, as suggested in Oki and Reed. They, for instance, suggested that neurons with a similar preferred orientation should be more strongly connected between them than neurons with different preferred orientations, and that this effect could control the selectivity of the system. Another question is whether, in fact, neurons in mouse or in rat are as selective as neurons in cat or monkeys. For doing that comparison, we need to define a quantitative measure of selectivity. We are going to use the orientation selectivity index. The orientation selectivity index is a ratio between the modulation of the tuning curve and the mean value, and it's defined in terms of the Fourier expansion of the tuning curve, where I can use f of theta will be f0, f1, f2, etc. Is the quantity I want to measure. If I have a neuron that is non-selective, I will have an OSI equal to 0, and on the other hand, I will have OSI equal to 1 if the neuron is totally selective, meaning that it will be active only for one specific value of the stimulus. So let's see the histograms, right? In mouse, B1, we see a significant selectivity that is about 0.4 in mean, that is lower than in cat. In cat, it's about 0.8. However, there is a lot of selectivity in mouse in B1. Now, when we see the behavior of the neurons in LGN themselves, remember that are the neurons that feed onto B1, we see a quite different behavior. In cat, the neurons in LGN are almost non-selective. The OSI is very, very small. In mouse, there is some significant selectivity. The neurons in LGN have an OSI above 0.2 in average. So, on one hand, we have a system that is more disordered, having salt and pepper, is less selective in B1, but is more selective in LGN. The fact that the neurons in LGN are selective to orientation has also been verified by mapping directly the spatial structure of the receptive field. This is in the paper of Zhao, where he studied a receptive field, the structure of receptive fields using reverse correlation methods, and he finds typically that the structure is elongated, right? It's not circular as one would expect naively from the figure of Hubel and Wiesel. There is a broad distribution of aspect ratio of these elongated receptive fields. So the aspect ratio is the ratio between the long axis and the short axis of the ellipsoid, and this gives rise to a broad distribution of OSI. Here we see that the median of OSI for the LGN neurons in mouse is about 0.2, consistently with the results I showed before. So all these facts indicate that there are some significant difference between the visual systems of rodents with respect to the visual systems of cats or monkeys. And these facts generate a lot of questions. First, one could ask, which mechanism generates orientation selectivity in rodent B1? What is the role of selectivity in LGN cells? I mean, Hubel and Wiesel speculated that the arrangement of the feed-forward connections is relevant, but here we also have another source of selectivity that we don't know the role. Are specific connectivity patterns necessary to have selectivity with a certain proper organization? Or maybe it's simply that the fluctuations of some random connectivity patterns are enough to explain selectivity? If so, if the fluctuations are important, are final size effects important? I mean, it would be the same to have 20 connections, 100 connections, or 500 connections per neuron. And finally, there will be different behaviors for different temporal components of the response, F0, F1, etc. These essentially are the main questions that we're going to try to answer in the rest of the talk. First, I will present the network model with random connectivity. Yes, this model includes first a layer that represents the LGN, and then another layer with two populations, one population excitatory and one population of inhibitory neurons. Typically, the stimulus is a drifting grating with an angle theta and a wavelength lambda. Also, later we will also use another type of stimulus. So the main hypothesis of the model is that the probability of having a connection depends only on the relative distance between the neurons. This is both for the feed-forward connections that go from LGN to layer 4, and also from the intracortical connections in layer 4. So there are no specificity at all. There is no relation between the connectivity and the dynamical behavior and the dynamical response of the networks. Here we see an example of the feed-forward connectivity. We have the layer of LGN. There are red and blue cells. The red cells are the blue cells are on LGN cells, and the red cells are off LGN cells. I mean, this means a non-cell is the neuron that becomes active when the center of the receptive field becomes illuminated and not the surround. The off cells has the opposite behavior. And again, the connectivity is simply random with the probability of connection that decreases with the distance between the neuron. For B1, we simulate a two-dimensional system with estimated size of about 2 millimeters by 2 millimeters, in size of which we have B1, that is a smaller region. We do this, we don't simply simulate B1 in order to avoid problems with the boundary conditions. These 2 by 2 millimeters cover a visual space of about 140 degrees by 140 degrees. The scaling was taken from the paper of Kalatsky and Stryker. So the neuron, the network is integrated by NE excitatory neurons and I inhibitory neurons in a 2D network representing L4. In P1, we have NL Poisson neurons in LGN. We have KFF feed-forward synaptic inputs for each L4 neuron, and 2K recurrent inputs, K excitatory and K inhibitory. The dynamics of the neurons in layer 4 is given by a conductance-based model with a leak, a sodium, potassium, and adaptation currents as intrinsic currents, and also a recurrent currents that come from other neurons in layer 4, and feed-forward currents that come from LGN. The parameters of the model have been chosen such that the excitatory neurons are regular spikers and the inhibitory neurons are fast spikers. Now, the firing rate of neuron in LGN is given by this expression. We have on one side R0, that is a spontaneous firing rate, and then the convolution between a receptive field, that is R of XY, times the luminosity field, where the luminosity field, if the stimulus is a distinct rating, is the same expression I gave before. And then after we do this calculation, we apply the rectification in order to have always a positive firing rate for the LGN cell. The receptive fields of the LGN cells are two Gaussians with different sign in order to have a center surround structure. There is the possibility of having an elongated receptive field if the variance in directions X and Y are not the same. The inclination angle of the receptive field is called theta I, and in principle, if there is elongation, we use an uniform distribution of these theta I's. Now, how are the interactions? The feed-forward interactions are simply conductance-based synapses with a time constant tau sin. So each time a presynaptic neuron generates a spike, it induces on the postsynaptic neuron a conductance that is this exponential with time constant tau sin. Cij is 0,1. That's the variable that controls whether there is or not connectivity between neuron J and neuron I. And as I mentioned before, the spike times of the LGN neurons are Poissonian with rate Rj of t, the expression that I showed before. Now, the recurrent interactions are also conductance-based synapses. Now, where the times are the times of the spikes of the neurons on layer 4, that could be excitatory or could be inhibitory. The strength of the connections is the same for all the pairs of neurons that are connected. I mean, where Cij is 1, and let us note that it's scaled as 1 over square root of k, where k is the average number of connections per neuron. We do this in order to have a well-defined balanced dynamics in the limit of large connectivity. In the lower panel, we see some examples of spikes of the neurons in the cortex and some postsynaptic potentials that all they have some realistic values of a few tens of millivolts. I mean, we choose the synaptic strengths to have some reasonable value of the postsynaptic potentials. So, what are the results for this model? Well, first, we simulate this, and the most important result is that we find that there is indeed selectivity. This is the firing rate the neuron of 3 neurons in excitatory neurons in layer 4 of B1 as a function of the orientation of the stimulus. Yes, there are there are 3 panels. Yes, this, and this one, and we see that indeed the response is selective. The firing rates are reasonable, of about a few hertz. If we plot the distribution of OSI for the whole population, we obtain panel B in the right. Yes, that has a mean value of about between 0.2 and 0.3. So this means that a purely random connectivity pattern can generate selectivity. This is the main conclusion of this point. Now, regarding the other question I had mentioned before, right? If this is purely controlled by the fluctuations of the connectivity patterns, what happens if we increase the connectivity? For instance, we can compare a network that has 25 inputs per neuron with a network that has 50 inputs per neuron, and with a network that has 100 inputs per neuron, and we see that in fact the selectivity does not change. Here are 3 examples of neurons with 25 inputs, with 50 inputs and with 100 inputs. And we see that there is always selectivity. In fact, if we plot the average value of the OSI as a function of the number of inputs, we see that at most there is a very good dependence on the number of inputs. Now, if we plot for the model the preferred orientation in color code on the whole network, we, as expected, we see a certain paper structure. I mean, neighboring neurons can have completely different preferred orientations. So, in some sense, this means that this model generates the main qualitative results that one expected: selectivity and a reasonable value of selectivity and a salt and pepper structure, right? But we'd like to see whether we have a more detailed comparison with experiments, and specifically whether we can find some qualitative difference with respect to the Hubel and Wiesel scenario. That's what I'm going to talk now. So in cats, one of the most interesting features of the response is that the preferred orientation of the neuron is invariant with respect to the spatial frequency of the stimulus. Yes, I mean, I can apply a grating with a wavelength of 10 degrees, 5 degrees, 2 degrees, 8 degrees, etc. So each one will be a different spatial frequency. And I can measure the tuning curve for each one of these frequencies. This experiment was performed by Webster and de Valois in 85. This is a quite old paper, right? And they found that when I change the spatial frequency of the stimulus, there is a very strong change in the firing rate of the neurons. I mean, the firing rate goes from 10 to 50 hertz, for instance, but the preferred orientation is essentially always the same. This is in the left. There is one example. In the right, we see another 4 examples where they plot the preferred orientation of the tuning curve as a function of the spatial frequency of the stimulus, and we see that at most there is a change of a few degrees, about 5 degrees. Now, what happens in the model when we do the same thing? Well, in our model, the behavior is completely different. In red, I'm plotting the tuning curve with a stimulus of 0.04 cycles per degree. That means that the wavelength of the grating is 25 degrees. With this with spatial frequency 0.01 degree. And if we compare the tuning curve, we see in both cases there is modulation, but now the preferred orientation of the stimulus has changed from one to the other. So it's completely different result with respect to we saw in the paper of Webster and de Valois. And these are not specific samples. We can plot for all the neurons in the network that have significant selectivity. We are plotting here, each point is one neuron, right? And we're plotting the in horizontal axis is the preferred orientation with the stimulus orientation of 0.04 degrees. And in y-axis, preferred orientation with the stimulus frequency of 0.03 degrees. The center one is 0.04, 0.02, and the left one is 0.04, 0.01. We can see that if the spatial frequencies are similar, then there is a strong correlation between preferred orientation. But as the spatial frequencies become more different, the correlation is totally lost. This effect can be quantified by evaluating this can be compared with experimental results. Yes, these experiments done in the laboratory of Nicolas Prive in Austin, where they measured the preferred orientation of the neurons with calcium imaging, changing the spatial frequency of the stimulus. And the upper panels are results of the model, and the lower panels are results of the calcium imaging experiments. And we see that it's compatible, right? As we take more different spatial frequencies, we lose correlation. Of the preferred orientations. This result can be quantified by evaluating the circular correlation coefficient of the preferred orientations. Here we should have 1, because there is a strong near 1 where there is a strong correlation between the preferred orientation, and here should be 0. Right? So if we compare how this correlation coefficient decays as we change orientations, we compare 0.03, 0.04 high, 0.02, 0.04 weaker, and 0.01, 0.04 that is almost 0. Here there are more experimental results. The green dots, sorry, are the results from calcium imaging, are the same as I showed before. The blue ones are results from electrophysiology. And the red and pink ones are from from 2 different models. The pink one is with circular LGN receptive fields, and the red ones is with elongated LGN receptive fields. So there is good agreement, but even in this case, we can see that the elongated model gives has a better agreement with the experimental results. Another comparison we did is to map the spatial structure of the receptive field. This was done by using what is called the Hartley stimulus. The Hartley stimulus essentially is some sort of Fourier representation of the stimulus space, in which each stimulus has a given value of wave number, kx, ky. So we apply this stimulus and we measure the response to this stimulus. Anti-transforming Fourier, one could obtain the model, the receptive field in real space. But in Hartley space, here we compare the model with experiments. We see we find what we call intricate receptive fields. They are intricate in the sense that they do not displace any trivial symmetry. And this reflects, of course, later in the fact that the preferred orientations should change when I change the spatial frequency of the stimulus. Here, the spatial frequency of the stimulus is simply proportional to kx squared plus ky squared. So it should not be some trivial function. Finally, we did an experimental comparison between the model and the experiment, but not looking at the response of the cells in B1, but at the thalamic input they receive. Right, I will go a little bit later about how this can be measured, but these are experiments from Lien and Scanziani, where they can measure these receptive fields, these thalamic excitation receptive fields. They use what is called some checkerboard stimulus, where there is at a given point one square that is illuminated and the rest is dark. So moving this point, they can map where there is activity when this square is illuminated or is dark, if there is less illumination than the mean. So they can map both on and off receptive fields. An interesting result is that the on and off receptive subfields of dynamic excitation are spatially segregated. I mean, they are two clouds of points, but are separated in space by some distance. The separation they find is about 5 degrees. There's a broad distribution, but in average it's about 5 degrees, and this is more or less what we obtain in the model. So we have some qualitative agreement in this, also in this aspect. So this means that, I mean, we have a model that gives rise to a lot of points where we can understand the experiments. This means that at least the scenario of random connectivity is not totally wrong, but we would like to have a better quantitative understanding of why the model works in this way. So in order to do that, we decided to study the statistics of dynamic input, and here I will show briefly some experimental, analytical, and numerical results. So first, how can we measure the dynamic input? This has been done by Lien and Scanziani. This is explained in a paper of 2013, where they silence the activity of the neuron in cortex, right, by optogenetically exciting the inhibitory neurons. So if the neuron in cortex cannot generate spikes, all the input should be coming from LGM. So by intracellular recording a neuron, all the postsynaptic potentials have to come from the thalamus. In this way, I can study the input itself to the network independently of the feedback connections inside the cortex. Well, they find that the behavior of this thalamic input is very different between if I compare F0 and F1 components. Yes. So this is in the left, we see one example cell. This is from the paper of Lien and Scanziani. F1 is remember that F1 is the component of the activity that is modulated with the frequency of the drifting grating. So we see that F1 is very strongly selective to the direction of the stimulus. What they call Q is in fact this Q is in fact F0, is the time average of the thalamic excitation, and it's very quickly modulated. This is one example, but if we do a population average, we obtain the panel. We obtain this panel. There is clearly a much more modulation in F1 than in F0. In fact, the OSI for the F1 component is 0.23, while the SI of the F0 component is 0.026. So it's about a factor 10 of difference. So this is, I mean, this is a non-trivial question. Why should be that the time average component is so different than from time modulated component, right? So we decided to study this analytically. Let us remind a little bit the structure of the LGN to L4 to the L4 system. We have couplings, Cij that are 0,1 independent random variables. The probability of having a connection is a Gaussian function with a width sigma ff. This is the width of this connectivity pattern. The luminosity field is a drifting grating with temporal with temporal frequency omega, wave vector k of theta, and the wavelength is 2 pi over k. The thalamic input will be simply the sum over the LGN neurons of Cij times the firing rate of neurons in LGN, that is Rj of t, multiplied by a constant that is a coupling divided by the square root of the connectivity. Here again we choose the square root to have a well-defined. Well, I mean, for convenience, I will explain this later. Now, what will be this quantity I will be a random variable because theseCij's are random variables. Now, what will be the distribution of this quantity? Well, the thalamic input will have a Gaussian distribution in the limit of large KFF. This is simply because of the central limit theorem. This distribution is fully determined by the average and the correlations because it's a Gaussian variable. We will study first, for doing the calculation, the simplest case where we call the linear case, where the rectification of the LGN cells is not important. I mean, if R0 is larger than R1, I will always have a positive firing rate, and I don't need to put the rectification explicitly. And also for simplicity, I will put circular LGN receptive fields. So R1 does not depend on the on the elongation of the LGN cell because there is no elongation. So in these simple cases, we can do the calculations. Yes, we can evaluate the mean value. We obtain that the mean value is J times the square root of KFF times R0. And for the correlation, we have some complicated expression that is J squared plus something. This something depends on one variable, on only one variable. It's called Z. Z essentially is something that measures the footprint of the feed-forward connectivity matrix with respect to the input wavelength. Yes, so in some sense, it's an adimensional way of measuring the width of the connectivity matrix. And we have this some expression, some quantitative expression for the correlations. So once we have the statistics, I mean, we have a mean value, we have correlations, we know that the Gaussian is variable. What we can do is generate with this statistical structure a lot of tuning curves simply doing extracting random numbers with these correlations. We generate a lot of tuning curves. We measure the quantity what we want. For instance, we measure the selectivity for F1. It is found in this case that selectivity for F0 is equal to 0. There is no selectivity in average. Now, if we plot the population average of the OSI of the F1 component as a function of sigma FF over lambda, we obtain this black line. This is an analytical result in the limit of the large connectivity. It's interesting to notice that the maximum value of the connectivity is about 0.22, 0.23. That is very similar to the experiment, to what obtained Lin and Scanziani in their experiments. Now, we can check whether we need up to which point the large KFF limit is necessary. We do simulations with KFF 25. Averaging over 10 networks, and we obtain the red dots. So it means that a KFF 25 is already a quite good value for having large KFF. In fact, we studied also a toy model with KFF equal 2, and this model also gives selectivity, right? I mean, depending, let's say we have one neuron, LGN neuron here and one here, X1 and X2. If the distinct rate moves in this direction, the response will be this one, that will be strong modulated. If the drifting rate moves in this direction, in the horizontal direction, the response will be completely will be completely different. And we can evaluate the average OSI, and we obtain the figure in the right. Now let's go to the most general case. What happens if the LGN activity is not rectified, and what happens if the receptive fields in LGN are not elongated? Well, this becomes a little more, the calculation becomes a little more complicated, but it can be done. We can take this expression that is the defining rate of the neuron in LGN. We expand in Fourier in time, right? And now we have an average component that depends on the elongation angle, an R1 component, and also we have R2 components, right? I mean, now there are higher order harmonics. So we will have selectivity in F0 and also F2 components. If we plot the selectivity of the F0 component, we find that indeed there is selectivity, but this selectivity is defined as effect, right? If we compare KFF 25, 100, and 400, right, we see it goes down with KFF. The selectivity of the F0 component, we also find that it's proportional to the elongation of the receptive fields in LGN. So, So if we have the selectivity of OC0 is proportional to the elongation of receptive fields, and essentially linear, and it scales as 1/square root of the connectivity. We also can see that even if the receptive fields are elongated and we have small size, the selectivity of the F0 components cancels out in the linear regime. If we increase the value of the spontaneous activity, we find that the OC0 decreases with increasing spontaneous activity. Now, for F1, the behavior is completely different. First, there are no finite size effects. Here are simulations, the analytical result and simulations for KFF 25, 100, and 400, showing that the OSI is always the same. And moreover, the selectivity of the F1 component does not depend on the selectivity of the LGN cells. I mean, here I'm going from 0 to 0.4 for two different sizes, and the selectivity of OC1 is essentially invariant. For the F2 component, we have selectivity, but again, there's a strong dependence on KFF. Here I'm comparing KFF 25, 100, and 400, and selectivity goes down as I increase the size. So what is the difference between F0, F1, and F2? This is a quite complicated thing, but essentially we can say the following: the mean value of each component is order square root of k. This is the mean value of the thalamic input corresponding to F0, F1, and F2. But the fluctuations are order 1. Now, the mean value is not selective to orientation unless there is a bias in the preferred orientations. But for the F1 component, the mean value cancels out because the equal contributions the on and off LGN cells. So the tuning curve is determined purely by the fluctuations. And the fluctuations are all the same order, so the OSI will be order 1. For the F0 and F2 component, there is no cancellation. So there will be in the denominator, I will have a term that is something order 1 plus something that is order square root KFF. This will give rise to an OSI that is order KFF minus 1/2. However, this is the thalamic input. However, this small selectivity can be amplified in the cortex. This is a more complicated thing that maybe we can discuss in the questions. Finally, this system has orientation selectivity but no direction selectivity, because a bar that moves from left to right and from right to right will give the same response. For having direction selectivity, we need a kernel that depends on time, right? If we take a kernel with a time constant of 30 milliseconds of probability p and 100 milliseconds of probability 1 minus p, with an expression that is given here, or this is the kernel, we can obtain some fluctuations ordered in the temporal response. Here I'm showing examples of tuning curves where, for instance, the response at 90 degrees and the response to 270 degrees are different if I have heterogeneity in the temporal kernels. We can quantify this phenomenon, this behavior, using the direction selectivity index, C1 over C0, where C1 is again defined by some Fourier transform of the tuning curve. And we find that as a function of the heterogeneity, this P, we have that the direction selectivity index, using purely random mechanism, can be up to 0.1. Let's observe that this leads to a small decrease in orientation selectivity index from 0.22 to 0.2. So finally, I want to finish. Let's summarize the conclusions. Random connectivity patterns can generate orientation selectivity and intricate receptive fields in B1. There are different behaviors for F0, F1, F2 components of the thalamic input. Elongated receptive fields in LGN cells are relevant for F0 selectivity. Finite size effects are relevant for F0 and F2 components, but not for F1. And heterogeneous temporal LGN kernels generate direction selectivity. So what we're doing now, we want to see how this scenario is modified when we put specific interactions. I mean, when the animal is learning or having plasticity, there will be stronger connections between neurons that do the same thing. How this will affect selectivity, and will this affect the value, the balance state in the cortex? Also, we want to have a well-defined prediction for the value of KFF, putting together a lot of possible measure predictions of the model to see whether we have a prediction for this quantity that is not really well measured. And also, finally, to go beyond salt and pepper, right? See whether or not there are some correlations in the preferred orientations of neurons that are very, very close to each other. This could be called could be called microcolumns. We have some preliminary results that indicate there are some very close range correlations in this system. Well, so let me finish mentioning where the collaboration. I mean, this work was done in collaboration with David and Carl, who was the author of the first of the paper I mentioned before. And the experimental result, the experimental work was done in the laboratory of Nicholas Prive in Texas, in collaboration with Shagruti Patatkal, that was at this point PhD students with Nicholas. And well, finally, these are the thank you for the funding from all these institutions.